Good afternoon, everybody. My name is Matt Leininger from Lawrence Livermore National Lab. I'll spend the time today talking about some of the recent deployments we've done over the last few months and even over the last 2 years at Lawrence Livermore with some partnerships we've had with QLogic and Dell. So we'll touch on a little bit. I wasn't sure how much people knew about Lawrence Livermore. We'll very briefly go over some of the projects and things we have going on at Lawrence Livermore. We'll talk about these recent cluster deployments we've done over the past couple years. And I'll show you some pretty early preliminary scaling and performance results we've seen on these clusters that are pretty phenomenal, frankly. So Lawrence Livermore, we're a DOE lab. We're under the National Nuclear Security Administration. We're just outside the San Francisco Bay Area in Livermore. We have about a mile square campus. As I said, we're under NNSA. Our computer building's right about there. You can't really see it very well though in that picture. So Livermore, we have a long history of deploying very large systems. Over the last 5 years, we deployed ASCII Purple, which was the first 100 teraflop machine. We recently decommissioned that. We've been involved in the development of the Blue Gene architecture over multiple generations, and we've also been involved in scaling up Linux clusters and deploying them as production resources within our environments. So today I'll focus, of course, on the Linux cluster side of the house. This just gives you a snapshot that we have quite a bit of computing at Livermore. It's not one big system, it's multiple systems. As you can see here, it's very much dominated by quite a few Linux clusters. If you just look down here for Linux or TOS, actually mostly TOS and InfiniBand, you see we have quite a few clusters, both our open and closed environments, spanning about 2.5 petaflops over the last few years. So our recent deployments, we've deployed about 3/4 of a petaflop, again, over the last couple years. Most of them have been within the last 4 or 5 months. So that's close to 7,000 nodes we've deployed, about 4,000 of those for this year, about 3,000 last year. And as I'll show in some of the architecture diagrams, it really spans the range from Leininger to Westmere, from InfiniBand double data rate to InfiniBand quad data rate. So the projects we've had going on at Livermore, 5 of them this year have involved our partnership with QLogic and Dell, all of which involve InfiniBand clusters anywhere from about 300 nodes up to 2,000 nodes. So it spans quite a range. And as I'll show you in how we design these Linux clusters, we build them very modular. So as our programs come to us and ask us to build clusters for them, we can build them of varying sizes, but keep them very similar as well, to make both the management of them and the stabilization of them go much smoother. So the one of them you hear about is, the biggest one is called Sierra. That's about the 2,000 node machine. We have a couple that are in the 300 node range, one that's in 1,200 node, another one that's in about 1,300 nodes. So one of the aspects that makes us to be able to scale out not only scale out these clusters, but deploy a lot of them. Not only Livermore, but we partner up with Sandia and Los Alamos in some of these deployments across the tri-labs, is that we have an operating system that's based on Red Hat Enterprise Linux. It's called TOS. We basically take RHEL, work with Red Hat, and put around that a lot of our own open source utilities for managing the clusters, parallel file system, which in our case is Lustre. We may provide some updates depending on what version of the Open Fabric stack we use and those things. Our resource management, Slurm, which is developed in-house, and Moab as well. And we have a variety of expertise in-house around the new hardware. We're always testing out the software stack on new hardware, working with Red Hat to make sure we can buy the leading edge clusters and have the software that works on it. So this is a pretty critical component. We stick to open source as much as we can. We don't dive into the proprietary stuff. So we're very fond of the Open Fabrics stack, the Open Fabrics Alliance. We help set that up, and we continue to develop within it and use it daily. So how do we go about building these clusters? Well, it's nice when you're building clusters to think of it as some sort of Lego building block. Instead of thinking it as a monolithic 1,000 node machine or 2,000 or smaller 300, is there a way I could come with a Lego building block that allowed me to be very flexible to build out whatever size cluster I want? So we came up with this concept that we called the Scalable Unit. In this case, this one's for a machine called Coastal that we built about a year ago based on 2-socket Intel Leininger nodes. And what you see here is that we defined it based on 144 nodes as a scalable unit. 138 of those nodes are for compute. We use one node where the users get to log in, of course, compile, do all their normal stuff. Another one's a management node. And the compute nodes have no direct access to the parallel file system. They get to that parallel file system by going through the InfiniBand network and then out through these 4 gateway nodes out to whatever SAN environment you have, which in this case was 10 gigabit Ethernet to get to our Lustre parallel file system. So this gives us a very simple building block, whereas if you want to build a small cluster, maybe just one scalable unit, you just drop this on the floor. If you want to build multiple scalable units, say 4 or 8, you just drop that many of them down. You need the extra tier of switching. So the switches in here, you basically have 144 ports going down to all these nodes and 144 going up. So you can build the next tier of switching, which we'll see. Here's some specs. It's the pretty basic layout that you're pretty common with Nehalem in terms of performance. And we had 24 gigabytes per node. We typically stick to about 2 gigabytes of memory per core at least. In this case, we're able to get more than that. So this is the coastal machine. It's 8 of these scalable units. You then tie it all together with 4 288-port core switches. We typically used the smaller leaf switches here on the edge. For the InfiniBand DDR days, that was a 24-port switch. So this is about an 89 teraflop cluster. It was dedicated, and I'll get into this a little bit more, it's dedicated to one of our programs in Fusion Science, and it's really allowed them to do some pretty incredible calculations over the last year or so. So when you scale all this out, you see the totals there. Since you have 4 gateway nodes that take you out to the Lustre parallel file system for each scalable unit, you got 8 of them, you got 32 total. As you scale out the machine, you also scale out the login nodes, of course. Now you have 8, as well as the management nodes. So that's what makes it a very easy building block if you want to scale out from small, say a couple scalable units out to 8 or 12 or more. So the latest generation that we've done is based on, of course, the QLogic quad data rate InfiniBand equipment. We moved to the Intel Westmere's. These are still 2-socket nodes, so 6 cores. The switch ASIC changed in this generation, so instead of the 144 nodes per scalable unit, it made sense to bump that up to 162. But it's the same general idea. You have half the number of ports going down to all these nodes, half going up. You keep the same number of gateway nodes, management login, but you just get a few more compute nodes in that case. Again, you see the specs here. It's the pretty standard 2.8 gigahertz Nehalem. We stuck to the 2 gigabytes of memory per core again. In this case, which is what our applications folks like, we certainly got a boost in the memory bandwidth performance, which that's one of the aspects you'll see in some of the performance graphs that I have down the line. So we can take this scalable unit design, and in this case, scale it out to however many we want. In the case of our largest machine called Sierra, we scaled that out to 12 scalable units. For another machine called Mir, we scaled that out to 8. So in the case of Sierra, that was 261 teraflops, which is the largest one we have. This looks very similar to what you saw for Coastal. So there's no huge change besides the slight variation in the InfiniBand QDR, the number of nodes and stuff. So this ends up being 1,944 nodes. We deployed 4 of the clusters I mentioned before. So the largest one is Sierra that I mentioned. That's a little over 23,000 cores. Mir is 8 scalable units, about 15,500 cores. And then 2 smaller machines, about 4,000 cores each. But you can see it's the same scalable unit design. So in terms of working with our integrator, they're just cranking out these scalable units one at a time as they're delivered, or multiple ones at a time in some cases. They get delivered to Livermore, we wire them together, burn them in. We have a process for doing that fairly quickly. So it's very straightforward, although it's still a lot of work. It's a very straightforward concept that allows you to maximize the time to getting these machines into production. So I mentioned that the Coastal machine is dedicated to one of our fusion energy programs. So that's the National Ignition Facility. I don't know how many of you have heard a lot about this, but this gold thing in the middle, you can kind of think of it roughly as like a Pringles can with the holes cut out. It's of course very, very small. But then there's a little, think of it as a gel capsule in there that has hydrogen, deuterium, or tritium. You have 192 lasers that hit the side of the hologram. They generate X-rays, and those X-rays compress the pellet. You get fusion. At least that's the idea. There's an awful lot of physics that goes on here, from the laser propagation. You're going through a gas, so your laser is generating plasma. There's laser-plasma interactions. There's the interactions with the laser on the material, blazing the internals of the hologram, generating the X-rays, compressing the capsule. There's all kinds of physics going on here. So this is a very complicated simulation. And in fact, they can't actually simulate this whole thing. Even using some of the simplest physics, we figured out that they need their application to perform at about a sustained 8 exaflops, just to be able to do the simplest level of physics for this entire picture you see here. So they often do subsections of it today. They've done quite a few results on Coastal over the last few years, and I'll show you a little bit of performance here that they got out. So the code is called PF3D. The first numbers here from an older machine we had called Hera. It was a 4-socket AMD quad-core node, so 16 cores per node at double data rate. And we see jumping from that to essentially keeping the same InfiniBand network, but going to Nehalem. It's a much sweeter balance, going with 8 cores per node and double data rate in that case. Jumping to Sierra, and this is where we really jumped into the full QLogic fabric, both HCA and switches, when we get to QDR. And you can see, even though we're adding quite a few cores, or 4 extra cores, 50% more cores per node, the network communication time actually went down almost by a factor of 2. Even though on paper DDR and QDR are a factor of 2, you'd hope to get a factor of 2, but you never do. So it's very rare in practice to actually see that, but in this case we did, which is pretty phenomenal. You see here that the CPU time didn't really change too much. Again, all these jobs using the same number of cores, so it's kind of normalized to that metric. But just slightly, so there was a little bit of a memory bandwidth improvement here. We also played around and ran Sierra only using 8 of the 12 cores per node, so that you're still using 4,000 cores total, but the same number of nodes between these two simulations. And again, you see the communication time went down even further, almost again by a factor of 2 compared to Coastal. So the network performance on this app, which is very intensive on the network, is extremely impressive that we actually got that amount of communication performance boost out of Sierra. So some other of our applications folks from the climate side, they're doing quite a bit of work on looking at regional climate models. One example here is if you look at these pictures here, you can see as you go from 2 degree on the upper left to 1 degree resolution on the upper right, and then down to half a degree on the lower left and a quarter degree on the lower right, you're slowly actually seeing that you can simulate the smog in LA, which something like that is pretty important, if you're looking to do regional climate models. So they need the quarter degree resolution in their models in order to actually see the smog in these regional climate models. So that sets their metric. And if they look at the performance they've seen on several clusters, so Atlas is an older 4-socket AMD dual-core cluster with double data rate InfiniBand. As they move from Atlas to Sierra, they saw a huge performance, so basically a 3x performance boost in terms of throughput. Then they were able to scale up as well. So not only use 4,000 cores, but move up to about 7,500 cores. They saw very good OpenMP scalability. And overall, they're getting a 4.5x throughput increase on Sierra compared to what they got on their older machine Atlas. This also allows them for the first time to begin thinking about running more simulations with even more detailed chemistry, which is what they need to add in to get a lot of the smog effects in there. And so because of the scalability out here at about 7,500 cores, they were able to add that in. You see the time here on the right went up a little bit. That's because you got more physics in the calculation. But they're still able to get this dramatic performance increase. So this is basically the number of seconds it takes on the simulation to do a CPU, a simulated day, so to speak. So this is another graph we have of the Sierra performance. So this one's very interesting. This is one of our codes. It's really one of our workhorse codes. It's one of our most complicated multi-physics codes. And the scalability of it is usually, it can be very harsh, put this way, on systems. And This is a historic graph of many systems, but what I want you to really look at is this bottom curve here in the blue. That's Sierra. So on the vertical here is grind time. The lower it is, the better it is. As you move to the right, it's scalability. So the flatter it is, the better it is. This is comparing Sierra here. You see in here there's some older Linux clusters. This red line is actually a Cray XT system. These blue lines are some Blue Gene systems. Some of these up here are some older Linux clusters and older power systems. But to date, on this very intensive application, Sierra is the best scaling machine we've ever seen. We're still analyzing what all effects of or features of the QLogic network are really enabling this, but we certainly have several ideas. We're continuing our analysis right now, but the scalability of the IB fabric is certainly the best we've seen of any machine of this type, out to about the 24,000 cores of Sierra. The latencies we're seeing on the fabric, certainly when it's not real congested, is on the order of 1 to 2 microseconds, which is very good across a 2,000 node machine. We're also seeing the message injection rate, how many messages you can push into the network at a given time. As you look at the small, kind of a 4-byte type message, is really, really high. We think that's part right now of what we're digging into in the analysis of what's really giving us the scalability, both the performance of the MPI collectives, which we're starting to look at, benefit from that dramatically. I don't have data on it yet, but we're also looking into advanced routing features, congestion control features, and toiling with them to see if we can get better performance out of the network as well. We've also been working very closely with QLogic in their PSM layer. That is, I think, a big part of why we're getting this good performance, is now released in open source and will be available, or is available now, I think, in the Open Fabric stack. So those are some of the basically the highlights, what's been going on at Livermore and where we're at with these clusters. We're looking forward to using them. Most of them are either pushed into production now or on the verge of getting into production. So our users are very excited and starting to test their applications and scale out, doing even more tests than I've mentioned here. So with that, I'll be happy to take any questions.